Hi, welcome to today's lesson. It is uncertainty and percent error. Our learning target today is I can determine percent error. So, starting off, what does it actually mean to be accurate? Now, we can say that means you have the right answer, but that's its definition in real life. But in science, accurate is the closeness of a measurement to the true or the accepted value, which kind of sounds silly. But if you know what accepted value means, it'll make sense. The accepted value is the number or the quantity or the measurement that all of the scientists in that field have pretty much agreed upon, and we consider that scientific fact. So, this is like the density of aluminum, for instance. Pretty much all scientists can agree on the density of aluminum. It should be the same in America, in Japan, India, France, Brazil. It should be the same essentially everywhere. Once we get scientists in different parts of the world to publish papers and kind of say, this is the number I got, this is the number you got, let's agree on an accepted value, that number then gets published somewhere. It may get published in the book called the Merck Index, which is kind of like a chemistry dictionary. It's the thing that'll be published in textbooks, on reference pages. If you were to look up that particular thing on Wikipedia, for instance, that information would more than likely be there. So that's what accepted value kind of means. The reason scientific fact is in quotes is because we are just people trying to measure and quantify nature. So our scientific fact is kind of just what we agree to, not necessarily a fact. It's kind of silly in science because if somebody gets data or information that undoes everything that we've learned with some new type of technology, say that we get a new telescope or a new microscope or a new thermometer or some other form of measuring technology that will undo all of the science that we've already done, that's a good thing. It's a step in the right direction. We want to find the answers to the universe. But that's why fact is kind of in quotes, because we only know what we know and we don't know what we don't know. So once we all kind of agree on it, we call it scientific fact. And that number or measurement becomes the accepted value. So when you or I are doing an experiment, the closer we can get to the accepted value, the more accurate we are. So, for instance, if I don't know off the top of my head the density of anything, let's see. Oh, and this periodic table in front of me doesn't have masses. How beautiful. Okay, the density of aluminum is 2.7 grams per milliliter or per cubic centimeter. So if I did an experiment and I'm supposed to get 2.7, but I got 2.6, I'm okay. If I got like 8.5, I did something way wrong. That is not accurate at all. So that's really what it means to be accurate. If the answer is 2.7, I get 2.6 and you get 2.4, my answer is more accurate than yours because I'm closer to the accepted value. Okay. Now, this is kind of what a visual of accuracy looks like. So over here, on this first one up here, our X's are kind of near the target. So we're going to say that this one's pretty accurate. This one's not so accurate because they're decently far from the target. This one is not accurate at all. These things are all over the place. This one, super accurate. This one's hitting the target right here, bullseye. Now, what is precision? These ones on the bottom are precise. These on the top are not precise. The difference between the top and the bottom is that these X's are all kind of clumped together, where these X's are not. These X's are scattered. These X's are scattered. Precision essentially is how close those X's are to each other. In terms of science, It's going to describe the closeness of multiple measurements or its reproducibility. So, story. My third year of college, I took a class called quantitative analysis, which that course is essentially trying to figure out how much stuff is in your other stuff. So, for instance, I had to do an experiment where I was figuring out how much chlorine was dissolved in tap water. Sounds really boring. I loved it, but it's very boring to a lot of people, and I understand why. I got my measurements super, super, super close together. I think my numbers behind the decimal point, I don't remember the actual numbers, but to my understanding or to my memory, let's just make it up. The numbers were like 2.48, 2.51. And I have no idea what these units are on this, and I'm going off of memory. I'll show you a picture in class. I remember taking a picture of this because I was so proud of my precision. The next one we'll say is 2.52, and then maybe 2.53. These measurements are super, super, super close together. I was so proud of myself that these babies came out as good as they did. They are so close, 0.48, 0.51, 0.52, 0.53. Those numbers are crazy close. I had very high precision. If I remember correctly, these numbers were not the right numbers. I did the lab decently wrong. I think I was supposed to get double the amount. I think I was supposed to get somewhere in the 5 range, and I got 2s. Don't quite remember. But my precision was impeccable. So, that's essentially what precision is. Now, what does this mean in terms of a lab, the difference between accuracy and precision? Accuracy is how close you are to the right answer, and precision is how close your answers are to each other. So, how do we know that we have a good measurement? We want results that are both high accuracy and high precision. So, we're looking for this target right down here. High accuracy on the target and precise, all very close together. If we have high accuracy, it means that our methods that we used, or the procedure for the lab, they were good and brought the scientists, or you and I, to the correct answer. That's what accuracy is for. The precision measurement tells you more about the scientists themselves and how well they conducted their experiment and how consistent their results were. I think I forgot to underline this, and the word you're looking to write is consistent. I wish I could write on this and just go whomp, but I can't. So just know that this should have been underlined. So accuracy, at the end of a lab report, when we're talking about the accuracy of our data, the accuracy is going to give us a hint as to how good our procedure was, and our precision is going to give us an idea of how good our hands were really in the experiment. Now, the reason we have two different things here, accuracy and precision, this is for most scientists. Most of us are going to be reproducing experiments that other people have done. So unless you're doing research, you are going to be reproducing experiments, which is good. We need people to reproduce experiments so that we can have more and more data to give us an accepted value. There are some scientists who have no accepted value to go off of because they're doing something that no one else has ever done before. And those people are going to lay some groundwork. They're going to publish a paper. And then people all around the world are going to duplicate their experiment to try to find whatever that accepted value is. They're going to all do the same experiment. They're all going to be looking for high precision results within their own experiment and then compare to other scientists and groups and papers to figure out what a high accuracy answer would be. So we can calculate percent error in a lab. And I say to my students, this is essentially a measurement of how wrong your answer is, which is not really a fair way to put it because we're not talking about how wrong your particular answer is or I don't want anybody to think it means how bad of a scientist you are, because that's not at all what it means. When at some point during the school year, we're going to do the heat of fusion of ice. So essentially, we're tracking ice melt. It's a really boring lab. Watching ice melt is super boring, but it's a really good chance for us to talk about data and graphs and heat flow and all of the things that come with that. But the reason that everyone doing that lab is going to get a very high percent error is because the scientists who determined that accepted value were using really, really, really high grade equipment. They were using really great calorimeters that were very much insulated and thermometers that measure with more decimal points than the ones that we have in our high school chemistry lab. We're going to be doing this with double walled cups. Some of us may have styrofoam cups. I don't remember how we're going to do it. But any which way, it's not going to be as good as the big boy scientists who get to do it in a very high-tech, expensive lab. So our percent error is going to be really big. And that's fine. That just tells us that, hey, your equipment wasn't so great. So it looks like you don't know what you're doing, but really you get to blame it on the equipment. Other times, you just messed up, and that's fine. Messing up is part of science, and that's what percent error is for. You get a 200% error and you go, holy cow, what the heck? And then you go back and you look at it and you go, oh, I see, I made a mistake right here. And then you get to write about it. So everybody knows if you make that mistake, that's what happens. I think they said that was a Reese's commercial, right? They accidentally mixed peanut butter and chocolate and it turned out to be the best candy ever. Sometimes bad things happen, but we get to learn from them. So that's a cool thing. This is figuring out percent error. So the measured value is going to be the value that you come up with, you, the scientist. If your data book says that the answer should be 3.5, that's what you put here. The accepted value is going to be the one that all of the scientists agree upon. It's the one written on the periodic table, on the reference sheet, in a textbook, on the Wikipedia page, in the Merck index. Those are the accepted values. There are going to be some people who have this written a little bit differently. They don't have measured and accepted. They have the experimental value, which is the one that the scientist in that room came up with. Experimental and, I don't even remember. Experimental value and the accepted value, I think. Regardless, the New York State reference table has measured and accepted. Measured may sometimes come off as experimental, but that's okay. It means the same thing. You're plugging in the same values. Then this right here is a really bad absolute value bar. So your percent error should always be positive. Sometimes you'll subtract and this gives you a negative value, this top up here. It's supposed to be always positive, so it's in absolute value bars. So we're just going to do one example, and that's it. This says a student measures the mass and volume of a piece of aluminum. The measurements are 25.6 grams and 9.1 cubic centimeters. The student calculates the density of the aluminum. What is the student's percent error? And then it's letting you know that the accepted value, which you could have looked up, is 2.7 grams per cubic centimeter. So we are going to figure this out. The student, I'm just going to write real quick on my little page here and then slide you over because I don't want to copy the wrong thing. Oh boy. Actually, you may want to watch me do this. This is kind of silly sounding. I can't figure out how to scroll through this page. Do you hear my pen going crazy? Oh boy. Okay, I figured out how to add a new page. Here we go. Sorry for that. We had a mass of 25.6 grams, and we had a volume. This is why I wanted to look first. 9.1 cubic centimeters. So this is 9.1 cubic centimeters. So First thing we're going to have to do is calculate density, which you should remember back from 7th grade. 7th grade, 8th grade, I don't know, sometime in middle school. Density is equal to mass divided by volume. So in this case, we're going to do 25.6. This is horrible handwriting. Holy guacamole. Divided by 9.1. I can't do that in my head, so I'm going to use a calculator. We have 25.6 divided by 9.1, and we are getting for our answer, and I haven't taught you this yet, but I want you only to keep one decimal in this case. So for this particular answer, we are getting 2.8. The rules for this come later, how many decimals to keep. Can I use this? Oh, I didn't know I could do that. I'm doing this with a mouse. I have a tablet in front of me and I'm like screencasting it, and I didn't know. Oh, that's so cool. Okay, I'm sorry. That was kind of dramatic. I'm the worst. You can call me the worst. It's fine. Oh, there goes the dog. So our density is coming out to 2.8. That's our measured value. But our accepted value, it said back at that question, was 2.7. So if we do this math, we are going to do, and I'm just going to pull it up real quick to remind you, it's the measured minus the accepted divided by the accepted times 100. So if we were to do that, we would get 2.8. Oh, it's worse. Oh, it's not even showing up on my thing here. It's only on the computer. It's not on my tablet. Okay. Remind me to never do that again. This is going to be 2.8 minus 2.7 divided by 2.7 in absolute value bars times 100. So when we do this, I'm going to flip back to the calculator real quick. We are doing 2.8 minus 2.7. That gives me 0.1. I'm going to divide that by 2.7. And I'm going to multiply that times 100. The answer I get is 3.7. So this means my percent error is equal to 3.7%. The lower the percent right here, the better your answer is. So low answers are good answers. And that's the correct answer. It's 3.7% error. Now, this percent error, we don't necessarily blame it on the scientist. We don't necessarily blame it on the equipment. It's usually a mixture, and we talk about it a lot in our results discussion conclusion section about why our percent error is what it is. Puppy's getting fussy, so I need to go. That's it. If you need to replay, rewatch, go right ahead. If that's everything, then I will see you tomorrow. Have a good night.